So our next speaker is Sandip Trivedi, who also doesn't need any introduction. He is a professor in TFR for last 20 years and one of the dominant figure in Indian string context. He is talking about AMPS firewall and related topics. Please, Sandip.
Okay. Thanks a lot, Pallab. So, okay, well, thank you very much for this opportunity to speak. I don't know how well qualified I am, so there will be subjects or topics about which many of you know more. Please stop and correct me and interrupt me. That's part of this purpose behind this meeting. Well, I was told to sort of review some of the more recent developments, and what I thought I would do is start by telling you a little bit about the ideas of complementarity, which were developed by Toft and then later also by Susskind and various collaborators. And if you wanted to look at one paper, there are others. I've given some archive numbers here. And after that, I would go to the recent work of AMPS, Alamiri, Merolf, Polchinski, Scully, and the other S here is Stanford, which are in these papers. There's also a more recent paper, as Suvrad just reminded me, which I may not have that much time to talk about, but let's see, which is by Merolf and Polchinski. Then I hope to cover at least a little bit the paper by Maldacena and Susskind, which I liked a lot, which is this year, 1306, and end with a summary. Okay, so that's the plan. Now, but before I begin, there's a bit of a gap between where Gautam stopped and where complementarity comes in the discussion, so let me try to quickly plug that. Here is a Penrose diagram now of an evaporating black hole. Let's say massless, some massless matter fell in, that's drawn in green here. It doesn't have to be massless, but I've drawn it to be massless. It falls in, a horizon forms, I draw that in blue. Then Hawking evaporation sets in, you get these quanta which begin to come out, and if you wait long enough, a lot of it comes out, eventually reaches Cry plus, and the black hole evaporates away. So this is the diagram you get. Now, Gautam reviewed Hawking's calculation, which shows that if you start with a pure state in Scry minus, okay, so start with the pure state, on Scry minus, then what it seems what you get here is a thermal state in Hawking's calculation. Outside the light. All right. Sorry. Sorry about that. Staying within the light cone, but going up to Scry. Okay, Hawking said that what you get on Scry plus is something which his calculation shows is thermal on Scry plus. And of course, this started really the whole discussion because people then said, okay, you form this black hole, it evaporates completely away. You started with the initial state on Scry minus, you have a final state on Scry plus. Is it the case that the final state as Scry plus is really thermal? Is it mixed? Okay, so is it really the case that a pure state goes into a mixed state during Hawking evaporation? Okay. Does a pure state?
What is, if you use affine parameter, how much is the width on Scry plus when it receives the Hawking?
It's on Scry plus. It's what the width corresponding to the Hawking evaporation time.
Yeah,
MQ.
yeah. That will be the width. That's in the affine parameter. That will be
that would be in terms of the natural affine parameter. That's right. Yeah, Penrose diagram, of course, distorts things like that. Right. Does a pure state on Scry minus evolve into a mixed state on Scry plus? This is the key question This is called the information loss question, okay? Because if that happened, if a pure state went into a mixed state, which is not allowed by the usual rules of quantum mechanics time development, because the Hamiltonian is Hermitian and time development is a unitary process, a pure state must go into a pure state in quantum mechanics. So if this happens, you would have information loss. For example, you lose the information of which pure state you started with if you're going to end up with a thermal state, okay? So you would have information loss, and there would be a big violation of quantum mechanics. So if yes, then the consequences are quite drastic, but it seems as if Hawking's calculation would give you that answer. And so this was really the beginning of the whole controversy or discussion, and various people felt that perhaps it was the case that corrections to Hawking's calculation, which might be small quantum by quantum, Hawking quantum by Hawking quantum, but could build up, let's say, such corrections might actually mean that the full state on Scri plus in fact looks pure. So that if you looked at some small section of it, it looks very thermal, but when you construct the full state, it is actually pure. More or less like what might happen if you took a lump of coal that hypothetically was formed out of a pure state and allowed it to then burn up. You again would get something which looks approximately thermal, but there we have no doubt that quantum mechanics should work the way we expect it to. The state should be pure. So people thought maybe here too the corrections would unitarize the final answer. Okay.
So in the boundary, I will have two kinds of modes, which will get reflected by the potential here, and which will go through the horizon and come out, right? So the modes which are reflected, they are like, we know from the quantum mechanics what are their frequency, etc., because they are reflected from the potential. And
ultimately, the black hole evaporates away completely. Then all that you have, okay, is stuff outside the black hole. The black hole has gone away, and in the spirit in which we do particle physics, what you ask is, you stay very far away, something from very far away went in, something comes out. Is the stuff very far away which came out? In general, on Scri plus and time like infinity, is that together unitarily related through a unitary transformation to what went in? Okay, there's no black hole at the end of the day because Hawking told us it evaporates away. So this is a very sharp way to phrase the question. You can be completely outside, you can be at Scri very far away, and you ask, is there a unitary matrix which relates the state at Scri minus to Scri plus? Yes or no? At least the question is conceptually very sharp. Okay. So this was...
About these things that get reflected from the potential?
yeah.
But as long as there's something that's coming out as thermal, you're still in trouble.
Oh, sorry, I thought you meant there would be stuff inside and so on.
So I think he was worrying about things that never reach the black hole but get reflected by the
Oh,
potential
okay.
rallying force.
Then they too would reach Scri plus, and you would include that in the total state on Scri plus.
So the way that you answered this question initially gives the impression that actually the singularity is not important in the description of the information loss paradox. Is
Well,
that a fair statement?
I mean, the singularity does not have to be involved in stating the question. The question can be, you stay very far away at asymptotic infinity, you ask about the initial state and the final state, and is there a unitary transformation that relates to two, yes or no?
But could I replace the geometry, for example, with a Rindler horizon rather than a black hole horizon, and can we set up the question in that framework?
If you took flat space, you could set up the question. If you took flat space and tried to break it up into Rindler wedges, you could ask, if you take part of this space, you want to relate it to part of this space, is there a unitary transformation? Nobody would say there should be one. If you take all of Scri minus and relate it to all of Scri plus, people would say yes, unless you're forming a black hole. So the question is a general one which we ask in particle physics, in to out, and it's a precise one. Okay.
Sandip, sorry for interrupt. Just to understand the connection between the Gautam's talk and the,
Okay.
in the Gautam's talk, some states in J minus, like vacuum, is rewritten by some, entangled states, right? B and C. And in that sense, some very complicated states can be written by some unique, pure state by using some other state. And so here, can you, how can I say? My question is, how can I say?
Are you saying that a pure state locally might look very complicated, or
I think what he's saying is that there was a purification possible in what I said. Okay, after all, the thermal density matrix was the reduced density matrix coming from some pure state, which was a highly entangled state. But that trick is not possible now because there is no inside. So what would this be? I mean, if you wanted to purify the final state, okay, how would you write this as an entangled state, entangled with what? I think that is.
Oh, I see. Yeah.
So if you have a reduced density matrix which is thermal, so be it. You can't purify that.
On the outside, what Gautam showed was that the distribution of photons coming out was thermal. And the worry is you add up those thermal photons coming in over time till the black hole completely evaporates, and then is the full state thermal or not? If it's thermal, then you have information loss. Or maybe there are corrections, etc. Okay, so this is the question, and if the answer is yes, it's it's a dire consequences for quantum mechanics, and because of this, various people thought that perhaps there can be corrections, and in the end, they make the answer on Scri plus also a pure state. Nobody has been able to do a calculation which actually shows that, okay? Nobody has been able to do it, but this was the feeling, okay?
Corrections in what?
Corrections in what? Good. Corrections to Hawking's answer for the state on Scri plus. At least what Hawking, if you take his calculation, showed was that you get here a state where photons were populated as per a thermal population. And maybe that was true if you looked at some photons. So let's say you had a state here on Scri plus. Maybe locally, if you looked at the photons in some region, they are indeed looking thermal. But when you look at the full state, there are long-range correlations in that state which actually make the thermal state, in fact, pure. So there could be long-range correlations or long-range entanglement which purifies that state. How do they arise in terms of an actual calculation? That's right. Nobody has actually done a calculation to show this, but the general feeling, for example, that Tuoft had was, and seems to be some truth to it, was if you took one of these modes that Gautam was talking about, let's say we took a wave packet from here and we try to propagate it through, oh sorry, it has to come out. So you take a wave packet here, so this is the horizon, you take a wave packet here and it barely makes its way out. And finally ends up here, this is the wave packet or the corresponding photon modes which would appear thermally populated. In the course of going out, it actually encounters the infalling matter. And if you compute the relative energy, given that it has some frequency of order the Hawking temperature at Scri plus, then it's a very large invariant energy, trans-Planckian actually. And so the hope was maybe corrections because of such scattering might give some kind of a unitarization. And yeah, go ahead.
Why don't we get rid of the trans-Planckian problem by doing this whole thing in a localized setup? So not by using the Hawking's derivation, but by just thinking of the late part of the geometry, much after the collapse has happened, somewhere near where you've drawn the singularity. You just think in that region, and now I'll do the derivation locally by saying this locally, this looks Rindler space. and I get some, and then I never talk about these modes that came from the far past, right? Because as you say, they're transplanckian. Can't we then get, put the Hawking derivation on a firm footing by doing that?
You might try to do that, but the modes which get out would have had to skirt the horizon, and if you propagated them back, at least encountered the collapsing matter.
I don't want to propagate them back, right? Because that's an unreliable propagation. I don't, as you say, maybe they came from that, or maybe there was some transplancking effect. All I want to say is that there is some radiation that's being emitted from the black hole that looks thermal, but I want to make that derivation in a local sense without tracing the modes all the way back. I mean, why am I forced to trace the modes all the way back?
Okay, we can talk about it more, but the precise question is one which relates Scri minus and Scri plus. That's the really precise question. And to answer that precise question, you want to take modes from here and see what happens to them here. You want to take the state from here and you want to see what happens to it there. And then you have to encounter this issue. I'm not saying, we should talk about it more. Let's take, yes, please.
You want to work at asymptotic for obvious reasons. So do you want to also deal with remnants, or you're going to rule out?
So yes, there are a couple of possibilities. One possibility might be that the black hole evaporates completely away, you get information loss. Another possibility I was going to come to was that the black hole evaporates away completely, but as I said, corrections make the state pure. And a third possibility is that in fact the black hole doesn't evaporate away completely. In that case you have a remnant, and the remnant carries the residual information, which could be large. And that is a possibility also. So there were a couple of possibilities that were suggested, and remnants is certainly one of them, right? Okay, although we won't talk about it that much today. So, okay, so this was one possible answer. Another one, as I said, was no. A pure state does not evolve into a mixed state, but pure state on Scri plus, minus evolves into a mixed, evolves into a pure state and in that case, at least as far as the outside observer is concerned, as I said, you do this experiment, look at what comes out and goes in from far away. It's described by a unitary time development. So black hole evaporation is a unitary process from the formation and evaporation. Okay, that was another answer. There are others, remnants, etc., but let me not talk about them here. Okay, the complementarity point of view, which I want to talk about, arose as a consequence of taking this second point of view. Let us assume for now that in fact black hole evaporation as viewed from the outside is unitary, okay? If you make that assumption, then what these people realized was that there is a very, very important consequence of that assumption, which is the following. Let's take a slice, a nice slice that crosses the horizon of a black hole. This, I'll call such a slice, say, sigma. It's a smooth slice. You can, for a big black hole, make it stay away from the singularity. And you can draw such slices if you initially start with a very big black hole, such that most of the Hawking evaporation has come out already, and yet you are far away from the singularity. I won't prove that to you, but you can do that for a big enough black hole. So let's consider such a slice. Let's make the assumption that then the consequence is, just of assuming that the evolution is unitary on a nice slice like sigma, the usual rules of quantum mechanics must break down. I'll make this more precise in a minute. Okay? And let me now try to tell you how that argument arises. Let's assume that it's the contrary, that the usual laws of quantum mechanics do apply for time development So on nice slices like sigma, what I really mean is for describing the evolution from scry minus on to finally nice slices of this type, the usual rules of quantum mechanics must break down. So let's see how that happens. If the rules of quantum mechanics apply, then let's say we started with a pure state on scry minus. Well, there should be a pure state on sigma, and that pure state should be described by a wave function. So let's say we have a wave function on sigma which describes the state of the system. Okay, and let's say we started with some particular pure state on scry minus. So I'll use this notation. So let's say we started with some pure state phi1 on scry minus, and let's say it gave rise to a state psi1 on sigma. Okay, now I'll be slightly imprecise, but do grant me that if the black hole had completely evaporated away, then the state outside, there would have been no black hole, and the state outside would have been pure. Here, the way I've drawn the slice, it's not completely evaporated away, but most of the Hawking radiation has come out, so the state outside is almost pure, but allow me to consider it to be completely pure. That's a slight imprecision which can be corrected. If on this nice slice, which is drawn late enough, the state outside is completely pure, so that ultimately the state on scry plus is pure, okay, then what must happen? Well, this slice can be divided into two parts, okay? The region inside, maybe I shouldn't use in here. Sorry, just let me just get rid of this. Just say this is the state on scry minus. Okay, so this can be divided into two parts: the region outside the slice, outside the horizon, and inside the horizon. Okay, and if the state of the system outside is by itself pure, then the full state has to be a tensor product, okay, of something inside. This in now stands for inside on sigma cross outside. And since it came from 1, I'll label it with 1. So I start with a particular state on scry minus. I end with a pure state on sigma, which is moreover a tensor product. Okay? If this is pure, then it has to be a tensor product of this type. Okay, well, so far, good, well and good. But now let's see how the contradiction comes with assuming quantum mechanics. You could have started with another state on scry minus. That would have gone to, let's say, psi2 on sigma, again, which has to be pure, and that would also then have to be of this type, now labeled by 2. Okay, so far fine, you're having pure states outside. But just given these two states and the linearity of time development in quantum mechanics, now consider a state psi1 plus psi2. Maybe I can normalize it properly. Then pure. It won't be in general pure because there are correlations between the outside and the inside. The only way to make it pure is if the state inside, okay, is the same. If phi1 in and phi2 in are the same. If that were the case, then of course, so in general, let me call this, in general, the state in 2, by which I mean this state, is not pure on the outside. And what I mean by that is, trace over the inside and construct the density matrix, it won't be a pure state, okay? The only way to make it pure, for it to be pure, phi1 in would have to be equal to phi2 in. Because then, of course, you can write that whole state as a tensor product, which is this unique state. Okay, let me label it as phi1 in, 2 if you like, phi1 out, plus phi2 out. Okay, so then, of course, it becomes a tensor product and it's pure. But if this is not the case in general, it won't be pure. All right?
So this factorizability assumption that psi1 at sigma, so yeah, so what exactly is it? So you're saying there are very few Hawking quanta on the slice sigma, such that you know that the reduced density matrix outside is not thermal almost.
I'm saying suppose the state outside was pure. If the black hole had evaporated away completely, if I drew this slice, then the black hole is evaporated away completely. And if you have no information loss, we are exploring the consequence of this possibility, then the state outside would be pure. And so then this consequence would follow. Okay, so
Statement that phi 1 is the tensor product of phi in times phi out. Can you explain that a little bit more? Why can we write it as a tensor product and not?
yeah, I'm saying suppose it were the case that the state outside is pure. Then there's no correlation, there's no entanglement. Then that means what does it mean precisely? I trace over the inside, I construct a density matrix for the outside, and the density matrix is a pure state. That means the state can always be written as some pure state inside tensor product. Okay, so
Okay, can I just, so this is being done not at very late, I think, right? I mean, when the black hole size has become a fraction of the original size, but still.
yeah, so the state outside.
I mean, one will not be surprised if phi in is the same, right? Phi 1 is, because there is no phi 1 in or phi 2 in.
Yes.
But, so it has to be done at that.
It seems I'm trying to, yeah, it has to be done late enough, but when the radiation, most of the radiation has come out. And one way to, for example, make it.
You want to, horizon size to be big enough so that it makes sense to talk about this phi 1 in and phi.
That's right, that's right. And you can, one way to see that can be made is, let's say I feed a black hole with pure state and all, but one where the ingoing energy roughly matches the outgoing Hawking energy. And I do this for a long time. Then most of the, if the final state is pure, most of the entropy should have come out. But, you know, the black hole has some nearly fixed mass, so I can draw a nice slice through it. So, or you just start with an initially very big black hole and then.
Right. I mean, if you start with an initially very big black hole, then this factorization assumption presumably will not be true, because we know that if you take a subspace, right, there is an vacuum entanglement between the inside and outside. That's not relevant here?
No, that is very relevant to the whole story. I'm just saying, if you assume for a moment that the state outside is pure, then you would be led to this. Now, you could say, oh, the vacuum entanglement itself suggests that that may not be possible. And that's the heart of the matter, of course, and we are coming to it. But I'm slowly building up to that.
So just one more thing. I agree actually that in the end, I would like to question this tensor product thing, but there's an issue of how much the nice slices have to be stretched with respect to inside and outside, which may be important. I mean, in just that, you know, you want the nice slices to be drawn so that the matter inside is still very far away from the singularity and you can use semi-classical evolution, while outside almost half the black hole is evaporated.
Yes.
So in some sense, you know, there's a very large factor between time evolution inside and outside, which is also something that some people understand.
Yeah, you can, but I'm just saying you can set up a situation where the stretching happens, for example, by feeding a black hole at the rate at which it, it loses energy due to Hawking evaporation. This kind of thing was made reasonably precise.
But in that case, I think the nice slice will have a lot of matter.
The nice slice does have a lot of matter.
Will have a lot of matter.
Yes.
Right? If you continuously feed.
Yes. But you can check about the back reaction and so on. For example, in the context of extremal black holes, you know, that's something we've done. You feed it in and you check. Okay, let me go on. So unless something really remarkable happens, that the ingoing state becomes unique, just because it fell through the horizon, okay, you will, in general, if you just believe that information must be coming out, and you believe the usual laws of, let me start again. So if you just, if you take the assumption that quantum mechanics describes the evolution of slices, then unless something dramatic happens, namely it goes into a unique state. In general, okay, you cannot have a pure state on the outside. Okay.
So you said that, I mean, you are assuming that this is, I mean, you are claiming that it is a product because the outside is pure. But as long as the horizon size is finite, the outside cannot be pure, irrespective of Hawking radiation or something, right? Because we know that there is an entanglement, vacuum entanglement between inside and outside. So what if we say that this product state will make sense only when the horizon size itself has become very small? And then, of course, there is a contradiction because, I mean, the phi 1 in and phi 2 in being the same.
Yeah, but by then, most of the mass has come out into Scri plus.
Yes.
And if you're going to postpone the coming out of energy till then you will more or less be led to a remnant-like scenario, I think, where you'll have very little energy and you'll have to account for a lot of entropy.
No, I'm just thinking of this product assumption, right? I mean, irrespective of a black hole, whenever you have a surface, right, and you are dividing it the inside and outside, we know that the state is not a product state.
Right.
So is it?
So we know that, I agree with you, we know that the state is not a product state if we believe that the usual laws of quantum mechanics extend to slices like this. And what the complementary point of view had to give up was that assumption, for the reasons you're saying. You know, that I would say it in terms of the breach,
I mean, imagine that this remains entangled and the entanglement keeps decreasing as the horizon size shrinks. Just because the vacuum entanglement is
right, but what you could do is have most of the mass already come out by then. So then you'll have to account for most of the entropy coming out with very little mass left.
Ashok is making an interesting point, which is that the entanglement entropy is infinite. So, is formally infinite. You have to put some cutoff. So, in principle, you could pull out a lot of,
I know he's making that point, but I'm saying in the end, when you'll have to get it out, you won't have enough any energy or very little energy left. So you'll have to say that whatever finally brings it out will have to be very soft modes. Now, maybe you can do that. Maybe you can, in the end, be left with some very low mass object which carries a huge amount of entropy and doesn't either decay at all or decays very slowly because it's going to involve very long
No, I'm not even sure that I'm talking about it's coming out all at the end, right? I'm just saying that it comes out at the same rate as the horizon size decreases, right? The entanglement.
Oh, but then I think we are back to this problem because if, let's say you made a black hole of very big mass,
yes,
and I could draw this slice much later, then most of the masses come out. And if you're going to say that because it's not an exact tensor product, there is some entropy, then that entropy will have to reside in very little mass. That's all I'm saying. And now let's follow the subsequent evolution so that the black hole completely evaporates away and all that entropy comes out. Then,
meaning, all I'm saying is it's not exact product, it's a linear combination, right? And how many things are there in a linear combination depends on how much the area of the horizon is left, right?
Yeah. If you like, yeah, that's right. But, okay. If you like, I could try to draw a slice like this, which would touch the singularity. Now, the state, if the subsequent evolution from here to here is entirely in the outside, if the state here is pure, and you could do physics on these slices, then the state here would have to be pure. And that means now if I think of the state here and here, there has to be a tensor product. You might object to that because it touches the singularity, which is why I drew it a little away. But by drawing it a little away, the amount of mass I have left as opposed to complete evaporation is very small compared to the total mass. So,
but, I mean, that spatial slice also has a very, very small sphere at some point, right?
This one?
S2?
This one? No.
No, not that. The one
yes,
which goes
this one, yes.
Yeah.
Yes.
Right?
Yes.
So that one could imagine that could be problematic, right? Because
yeah, so you could argue there's a region of high curvature here. That's why I stayed away from that slice. And I rather would argue that on this slice, most of the mass has come out. If you don't believe in bleaching, you would still have most of the entropy inside or in the correlations. So
use the stage argument and estimate the average entropy. That might make the most sense.
Okay, let me go on. Otherwise I'll never get anywhere in my talk, sorry. Okay, so this is the point. Now, but the assumption that the ingoing state becomes unique is a very dire assumption too, because it is in conflict with the principle of equivalence. Because if this was how the issue is resolved, and the infalling state becomes a unique state, no matter what you started with, that phi 1 in and phi 2 in are the same state, no matter whether you started with psi 1 and psi 2. That means whether you throw in the Britannica or you throw in the Kannada Shabdakosh or Hindi Shabdakosh, the final state, on this nice slice, very far away from high curvature, is the same, is a unique state. And that is in conflict with the principle of equivalence. If you believe nothing special at the horizon happens, infalling observer sees nothing special, that shouldn't happen. Okay? So, the fact that phi 1 in and phi 2 in would have to be the same state, would have to be the same, is called the bleaching, have to be the same. Is called, or used to be called the bleaching, because it gets bleached of all attributes. Process or possibility, and it is conflict with the principle of equivalence. Okay, and
so the modes now you are talking about, modes that you are now talking about are only the outcoming Hawking quanta, not the infalling thing, right now?
Well, when I drew the slice sigma, it had both in and out.
By in, you mean just the inside
the
horizon,
the stuff
right?
on the inside, yeah.
So what I just wanted to know, sir, in the earlier talk, there was a boundary condition that we are specifying at the boundary as well as at the horizon, right?
Where is the boundary? Sorry.
At the sky plus and at the horizon, right?
At the horizon. That was for finding out what would happen here. Now I'm just looking at the whole slice. So this is the entire Cauchy surface, if you like, in its own right. So there's nothing else besides it.
I'm just asking, can I not arrange for some boundary condition which will make, the phi in always the same? I want the inside.
No. The phi in refers to this region. So anyone falling in, will hit it, and different kinds of infalling matter will hit it, and we would have to say, no matter what the difference is here, the state here is the same. So this is the point, that unitarity, as far as the outside observer is concerned, is really in conflict with the principle of equivalence if we believe that usual laws of quantum mechanics must hold on these nice slices. And the people who are thinking about complementarity says we like both principles. We want the evolution to be unitary as seen from the outside. We want the principle of equivalence to hold as seen by a freely falling observer, and therefore we are going to give up the fact that on nice slices which cross the horizon, you can do quantum mechanics. Okay? It's a very radical departure, but you are going to be, this is what makes the information puzzle so deep, you're going to be having to give up something cherished anyways. And they said, we'll keep these two, but we'll give up the fact that you do quantum mechanics on these nice slices. Absolutely. So yes. So let me just, and I will, I don't know, I'm running very slow, so let me not even break. Let me just tell you what are the postulates of complementarity, and we'll come in a minute to this question. So the complementarity, the postulates as stated, is that black hole evaporation, and I mean here as seen from the outside in terms of relating data on scry minus and plus, is unitary. The second assumption, let me put in a slightly modern terminology, infalling observer sees no drama, as it's now called, at the horizon. I call it principle of equivalence because you're in an elevator, you're just falling in. Why should something funny happen when you cross the horizon? We could be crossing a horizon right now. They put in another assumption, low energy, two more, effective field theory is valid near horizon in a semi-classical sense. That is, the horizon is a region of low curvature. You expand a field in creation annihilation operators, kind of like the way Gautam was doing, for the usual range length scales bigger than L Planck. And a fourth postulate, which is that to a distant observer, a black hole has a number of states given by e to the s Bekenstein-Hawking. Okay, so these were the four postulates they laid down, and their claim was no experiment you can do will land you in a contradiction with these postulates. In other words, their point was, we are going to give up the fact that you can do quantum mechanics on these nice slices, but you can do quantum mechanics sitting outside. Okay, in other words, on slices like these, which at first sight seem, more crazy. Let me draw them in another color. On these more Rindler or Schwarzschild-like slices, which don't cross the horizon. Here, quantum mechanics is okay, but we're going to give it up on those nice slices, and then we assume also there's no drama. You fall through, and locally you don't see any big departures from usual GR and relativity, and these two other assumptions. No experiment, okay, will lead to a contradiction. This was the claim between these. Okay, so that was the claim. Now to come back to what was said, it's true that this giving up this fact is itself a radical thing to do because we are invoking non-locality in a very important way. The physics locally on the slice, on the nice slice, is like in flat space. That was the whole point of the no drama kind of hypothesis. But you put an additional global part of information is given, that is, if the slice happens to cross a horizon, then we're not going to be able to do quantum mechanics. So that had to be put in, but you have to do something. Otherwise, you're not going to be able to reconcile no drama with the information coming out. Okay, so so this was the complementary point of view, and I don't know, I can. Well, I don't know if I've convinced you folks here, but it's very, if you want both these things, it's very hard to reconcile that with doing quantum mechanics the usual way. Now, of course, another possibility is you just say information is lost. That's what many people would say. But that has its own share of problems. So we are not, let's not take that point of view. You do this, and then you want, giving up, assuming certain, so of course, later developments will give this up. In a nutshell, the rest of what AMPS and so on have tried to argue is that there are contradictions. This view does lead, you can do experiments, etc., which lead to contradictions. Something must be given up, and they say we are going to give this up. We're going to keep this. And that's the firewall proposal.
I need to ask one question,
please.
actually, that these 4 questions are being asked in the framework of what theory? I mean, there is something on the back of the mind that there is a complete quantum theory of gravity.
Yes, there is, I think what's being assumed here is that there is a theory in which black hole evaporation is unitary. They also put this in. for various versions of experiments you try to do, this can be important. And so there is a quantum theory where both properties are true. And in that theory, if you also have this property that you don't depart radically from principal equivalence, then you're left with this. So nothing very specific, I think, needs to be assumed, but you do need to assume that this.
I just want to ask something which is related, just if this understanding is consistent with what you're saying. So let's say we say, as Penta said, that there's a holographic theory, and the space-time emerges holographically from that. So there's some conformal field theory. And now I say that I can make sense of this holographic space-time only to a certain accuracy for certain kinds of questions. If I ask questions that are too detailed or too accurate, then there's no sense in which this holographic space-time makes sense. Is that the same as this, or is there a subtle difference between what I'm saying right now? And that would also resolve this, by the way, because it would say that you can't think of this as a direct product, because in some sense the space inside is not independent of the space outside. The space inside is a rewriting of part of the space outside. Is that a subtly different thing from the historical understanding of complementarity, or is
well, if you're going to say that the state inside is a rewriting of the state outside, I think that in a sense is already departing from the usual way in which we do quantum mechanics. Because and I was going to say that, you're then saying I can have, roughly speaking, quantum cloning or doubling of information, and that is okay because there's no experiment that will land me in contradiction.
Can I say it in another way? I have some theory on the boundary, which is a completely well-defined theory.
Yeah.
And the same and now I have to construct a space-time from that.
Yeah.
The same information of that boundary theory appears in two different
Yeah.
parts and that is not, if I give you a
that
trivial
would be
example.
consistent with complementarity. They would say it is, in fact, let me just make this comment and then we must come back to what you say. So just a couple of comments. Okay, and then we'll just come back to what you say. A couple of comments. Why did they think there'll be no experiment that will lead them in contradiction? The rough thinking was it's very hard to communicate between the inside and the outside. Okay, and there's an obvious catch to that, which is what much of the talk will be about in terms of trying to come up with contradictions, which is, yes, you can't send a signal from the inside to the outside, but you can send one from the outside to the inside. And we are going to try and use that to come up with contradictions, okay? So that's the first point. The reason they believe this was hard to communicate between them. And then we'll come to what Surat is saying. Outside, but one can send a signal from outside inside. Okay, and that's what we will try to do. Now, the basic idea, I think, in terms of complementarity is, and this is partly why it's even called complementarity, I think, is that you have to give up one slice describing both the inside and the outside, because if you believe that the information comes out, then just the state on the outside already encodes for the inside, okay? Because whether you threw in the Britannica or you threw in the Shabdkosh is something you know about already by looking at the radiation outside, okay? That is why you don't want to be doing usual quantum mechanics where you're, in a sense, keeping double the information, okay? But you could just do quantum mechanics on the outside. That would be fine. Or you could just do quantum mechanics on the inside. That would be fine too, although it's a little less precise because you have a singularity. That would be fine too. You just can't do both together. And this is because roughly, I'll just complete and then please comment. This is because roughly, if you're going to do both together, you are going to allow for a cloning of information. The argument which says that in quantum mechanics you can't have cloning is very similar to this. It's just a linearity argument. Okay? And if you're going to allow for usual quantum mechanics, you're going to say, okay, cloning is going on and that will lead you into trouble. Unless you say, okay, I'll individually allow cloning to happen, but I won't allow the measurements done here to talk to that, to the outside. And that's the complementary point of view. So I would say that if you're going to have a setup where the inside is encoded on the outside, we should still ensure that there's no contradiction in the sense that someone who knows that the outside is carrying the information goes in And then, so you decode the encyclopedia outside and fall in. It shouldn't lead you into a contradiction when you meet up with the encyclopedia inside.
Yes, it shouldn't. But one might say that, maybe neither the outside, maybe just space-time is just not a very good description beyond a certain point. And you have some boundary operators which are well-defined operators. The same operators appear in an effective description of the outside and in an effective description of the inside. And you're right, you have to make it consistent with the fact that, commutators have to be small and so on.
Yes.
But that's you might not want to take the space-time picture seriously at all. You might not want to say that the outside gives you a complete description either, because there's no sense in which the outside is particularly precise beyond a certain point.
Yeah, I agree with that. And I think when various experiments are going to be proposed to land you in a contradiction with this idea that you can do quantum mechanics on the outside, you can have the information inside, and it's okay. If someone's going to propose, we must subject it to this check as to, could it be that our usual notion of semi-classical gravity gives way in that experiment, and therefore that experiment is not valid? Absolutely. And I think actually some of the outs are crucially tied to that comment. Okay. And perhaps to the imprecision, therefore, of the tensor product. Okay.
So therefore, you are assuming that in this so-called complete theory of quantum gravity, you are working in the semi-classical approximation. In all those four things that you talked about.
Okay. So actually, this was the second comment I was going to make, and it ties to what the second comment I wanted to make was, the tension is really quite deep between these two things, unitarity and no drama, so that one doesn't expect small corrections to take care of the tension. The state really has to be bleached. It really has to become independent of what was thrown in. So in that sense, small corrections to sort of an answer like that may not be enough. Yeah.
So that's the point I'm getting at, that if you do semi-classics, it's like large N expansion. So the expansion in, 1 upon Newton's coupling, and all those corrections actually may not pile up to actually resolve this type of issue.
Yeah.
I think something like that is at the back of your mind.
Yeah, as long as we have a smooth geometry, approximately smooth geometry, then it's not clear if that by itself will resolve it.
Also, when you say small corrections, what is the meaning of small corrections? Two wave functions which may look very similar, maybe completely orthogonal, right? I mean, it's like, if you take two momentum states whose momenta differ by a very, very small amount, right?
Yeah.
Are orthonormal.
Yeah.
I mean, if one change, so if this information is encoded in such small difference, would you call it small correction or big correction?
I meant, okay, in this context, suppose in some leading approximation, phi 1 in and phi 2 in were orthogonal states. Yeah, you say no, that's not enough. A small change can now make
it orthogonal. I mean, the point is it's.
But
yeah, but there are many quanta. Each quanta has such possibility, right?
Yeah, so you're saying that there phi 1 in consists of n states and phi 2 in are in different.
That's right. Yeah.
But I would say that Ashok, we would have to ensure that these have nearly unity overlap with each other for vastly varying, I minus.
The point is, locally they may look the same, right?
Locally they may look the same, but if they're not the same on the inside, not the same on the inside, when I try to, do some kind of quantization on the inside, if they're not nearly the same, then you'll get a lot of entropy if you trace over the inside. That is, suppose they were really orthogonal, and you then compute the density matrix, and if phi 1 out and phi 2 out are also orthogonal, you'll get log 2 or whatever in this case. And more generally, if you had n possibilities, you would add them up and get log n. So for most of the infalling states, the resulting phi 1 in would have to be, the resulting phi in would have to nearly have unit norm with each other, unit overlap, I think. Otherwise, rho outside for a generic infalling state would be having a big entropy. Okay, yeah, sorry. I have to speed up. I'm not sure how to do this because the questions are interesting, but this is the basic point of complementarity. Now, let me go on and say, where does the AMPS, so I'm only done with this, but never mind. Now, let me go on to more modern work and say, what do AMPS bring to the discussion? I'll keep this up. Small corrections don't change. The conclusion that you have to take a sort of complementary point of view. Okay, now let's go on. Let's go on to AMPS. Actually, the work of AMPS and AMPSS, which I'll just call AMPS anyway, is based on important earlier work by Samir Mathur, who really laid out the kind of thinking in terms of strong subadditivity and so on that I will talk about. All the viewpoints are quite different in some ways. This is a very important paper. And to discuss this work, I'm going to have to introduce two more concepts. So please bear with me. And I have to end at 12:30, is it? Okay, 12:45, great. And the first concept I have to introduce is of strong subadditivity. And the second is of page time. This is less important, but okay, useful in some ways, so let me do that. But before that, let me tell you what is the basic point that AMPS, etc., try to make. They look for experiments or for, they analyze the postulates of complementarity more closely, subject them to experiments, etc., and they say this is not true. Experiments the whole procedure does, when you try to implement it, does lead to contradictions between these different possibilities, okay, between these different postulates. So that's the basic point. There are contradictions between the postulates which are laid out, and they propose according to them, the resolution is that there is drama. At the horizon, very radical conclusion in its own right. And in fact, the horizon, which is a nice, smooth surface, the region around the horizon, nice, smooth region of space-time in GR is actually replaced by a firewall, a region which is a word for a region of high curvature. Actually, we are not very specific about what it is, but it's just a region which is not like a smooth region of space-time which you can fall through easily. High curvature, let's say. So this is the upshot, in a sense. I'll tell you how they try to get there. And we'll see the arguments. I'm trying to here present the work. I don't myself buy the arguments fully, I have to say, but let's see what they are. They carry weight. I think they should be taken seriously. So I'm going to have to introduce these two concepts. Let me do that. The first is strong subadditivity. And this involves entanglement. So what I really mean is strong subadditivity of entanglement. So let A, B, and C be subsystems in the same Hilbert space. So if you like subspaces, let SAB be the entanglement of A union B with everything else, okay, in the Hilbert space, with its complement, let's say. Okay, so you take A and B, this is a subspace, all right. What is entanglement entropy? You compute the reduced density matrix for A union B by tracing over everything else. You take minus trace rho log rho for that reduced density matrix. Okay, so just for once, S entanglement for any system A is minus trace the reduced density matrix rho log. And then you do it for AB to get SA. Okay, so that is what I mean by SAB and so on, SBC, SA, etc. Then strong subadditivity says if I take SAB plus SBC, that's greater than or equal to SB plus SABC. It's an inequality like that. I won't try to prove it here. Now there are some consequences of this, and that's what I'd like to explore, and then we'll use that kind of reasoning to sharpen various things and so on. Suppose, so let me introduce another. So now consider a situation where, now suppose we are going to use this in a situation where A, B, and C, just for simplicity, have the same dimension. So these are vector spaces in their own right, and they have the same dimension. Just for simplicity, say 2. So each of them is a qubit, okay, of dimension 2. We can then talk about things being maximally entangled. A and B are maximally entangled if, okay, A union B is pure. By that one means, if you compute the entanglement entropy, this is 0. Okay, more generally, it's a pure state, not entangled with anything else. So A union B is pure, but if you compute the entropy, entanglement entropy of A alone, then that is the maximum value, which is the dimension of A. Okay, so it's A is as entangled as it can get, but it's only entangled with B. Oh, sorry. Excuse me. Sorry. So A is as entangled as it can get, but only with B. Okay. All right, sorry. So these are a few definitions, but it's good. They help us being a little precise. And from subadditivity and maximal entanglement, which is really just a statement, what I mean by the term, it follows, now one can show quite simply, and I can do it in some lunchtime for you if you like, that if A and B are maximally entangled, then B cannot be entangled with C at all. And I'll tell you what I mean precisely. What do I mean by that? To check whether there's some degree of entanglement between B and C, for example, you could compute the entanglement entropy of B, entanglement entropy of C, and compare that with the entanglement entropy of B union C. Okay, if there's some mutual entanglement, that entanglement entropy of B union C should be less than this. But in fact, if A and B, if B is already maximally entangled with A, then leaves no room for any more entanglement of B. So this is equal to SBC.
This is assuming that ABC have the same dimension.
Actually, this is most precise. I think I might have to think a little bit, but it's probably enough if A and B have the same dimension. Then if A and B are maximally entangled, I think I'll have to look through my notes, but I think that's probably enough. Okay, so B, so this, the colloquial way of saying it is that entanglement is monogamous. Okay, once B gets maximally entangled with A, it's married off to A, then not only can B not be married to C, it can't even flirt with it. Okay, there can be no entanglement. Entanglement is monogamous. Okay, so, and I'll just take Subrat's question. If I've said something wrong here, please correct me.
I just want to say this. Another version of strong subactivity that makes this entirely clear, which is
Okay.
SAB plus SBC is greater than equal to SB plus SB.
SAB plus SBC.
The same thing is greater than equal to SB plus SB. Yeah. So that makes it completely clear that if SAB is 0, then SBC has to be SB.
Yeah, because you
ABC on the right hand side, this form makes it clear.
yeah, that's partly how. You can prove in general that SB plus SC must be greater than equal to SBC. This is intuitively obvious, also follows, and then from this you can prove SBC is greater than equal to SB plus SC, so the only possible, if SAB is 0, etc., then the only possibility is that. That's
you just don't have to worry about ABC.
Okay. All right. Okay, so so entanglement is monogamous. Okay, and so that is the first concept. The second concept I want to introduce a little bit is that of page time. So the idea of page time is to look at the, let's say we sit at Scry Plus, let's say we believe that information all comes out, let's look at the state of the radiation, and let me plot it in terms of the natural coordinate on Sky Plus must be U.
ABC together is a pure system, or that's
For the I don't think it. For that it didn't. I thought you were asking. Even I think here it doesn't really. Yeah. Okay. So let me look at the radiation which has come out on Scry Plus, and let me use, roughly speaking, a coordinate time. Gautam might have called it U or something, but basically which measures time as seen far away by a Schwarzschild observer or some asymptotic observer. What will the and I just have the radiation which has come out, okay? So I'm marching along here as time advances, that time coordinate, and I'm looking at the radiation that is coming out. First this much comes out, then this much comes out, etc. That's the advancing time. And I look at the radiation which has come out and I compute its entanglement. Okay, with everything that is to come out yet, etc. What will this curve look like? So here we have entanglement. Well, initially you had no radiation, so there's nothing to get entangled with. So the entanglement entropy must be 0. If you believe finally that all the information comes out, and if you started with a pure state, finally the entanglement must be 0. And so it must have some curve like that. Okay, and there's a time here where it peaks. That time is called the page time. Okay, and if you believe that the full system, black hole plus radiation as seen from the outside, is a pure state, because you started with a pure state, then the entanglement in the radiation must be equal to the Bekenstein-Hawking entropy of the remaining black hole. And so roughly, if you started with a black hole of some mass, the page time is when half the entropy, not roughly, the page time is exactly the time when half the entropy of that black hole has come out. Okay, so but it is when the entanglement in the radiation coming out peaks, and after that the entanglement starts to drop. If you have an old black hole, which is the terminology I'll use, sometimes that's a black hole much after it has crossed its page time. You formed it, and then you let it evaporate for a long time. You wait long enough so that most of the radiation has come out, okay? And most of the entanglement has come out. in the sense that if you look at the full radiation, then it has very little entanglement. Okay, so that's what happens for a old black hole, old compared to the age time. So let's assume for a moment that the full radiation state is pure. Then it's the entanglement. Actually, it's just the entanglement of the radiation which has come out. Sorry, let me just answer it precisely. You have some amount of radiation which has come out. You know, you're standing very far away from the black hole. It's evaporated for a while. You gather all the Hawking radiation, and you compute the entanglement of that subsystem. Subsystem compared to all the radiation that will come out eventually.
That you are saying that it's the entanglement of whatever the subsystem outside the black hole?
Yeah, so one could think of it two ways. One way to think of it is just look at, finally be at Scri plus,
yes,
and look at the subsystem up to some instant of time.
So you are dividing Scri plus into two parts?
Into two parts.
Yeah, and then you don't have to worry about the entanglement, vacuum entanglement across that?
You don't have to worry about that.
Why?
No, because I'm just looking at, let me assume that the black hole evaporates away completely.
Yes.
Finally. So finally I will have some state at Scri plus.
Yes, that's
and
right.
that's the full state of the system. And I can divide that state into two parts.
Spatially into two parts, yes.
Two parts, and look at the...
But once you divide the system into two parts, there is also the entanglement of the vacuum, right?
Across this.
Across this, yes. I mean, why is it that you don't have to worry about that? And particularly when you are applying this general formalism of strong subadditive, etc., these hold for good quantum systems, right? And the underlying quantum system here is the quantum field theory rather than just quantum mechanics of these particles.
Yeah, okay. Okay, good point. It's true that the entanglement entropy in a quantum field theory actually diverges if I break the system into two parts. But I think maybe we can try to make it precise as follows. There is a part of this entanglement entropy which will not change with time. There's a cutoff.
No, it will, because the area changes, right? The area of the event horizon changes as the black hole is evaporating.
The area changes, but what I'm trying to get at is, if you construct the full state here, then if I break it in parts, there is a divergent quantity contribution because of very short range entanglement,
yes,
which you're right, will be there. But if the full state is pure, there is a sense in which it gets pure because of long range entanglement between the quanta earlier and later. And so it's a good point, but to make it precise, we might take out the cutoff independent, the cutoff dependent quantity in an area, in a time independent way. You know, on Scri plus, we could put in a cutoff which doesn't change with time.
That's a little confusing to me because S2, right, at least the black hole horizon area is decreasing.
It decreases, but it could be, that should get reflected in long range entanglement here rather than a cutoff dependent quantity. I mean, so...
is that included in just the Hawking radiation part? That's what I'm wondering.
I mean, even if I had a pure vacuum, that term you're saying would be there. And somehow we are trying to measure the entanglement because the state is excited about the vacuum. Maybe we can try to make it more precise like that. That the entanglement entropy in a quantum field theory of an excited state minus that of the ground state is a cutoff independent quantity. At least some divergent contributions are probably cutoff independent.
Can I try and make it...
or we could talk of mutual, yeah. Yeah, then we'll have to think of the page time in that context, which I'm not sure. Yeah, I should go on.
I think there's one comment here which Ashok may be making, which is that the cutoff dependence is hard to get rid of because the mass inside is changing. So it's not like you can just subtract off area by something because that area is changing. Unlike an ordinary quantum, non-gravitational quantum field theory, where this would not occur. But
I'm sitting at Scri plus. What do I care? I'm sitting at Scri plus.
What's the definition of A, B, and C in this?
For
have to draw a line somewhere to say everything on this
for
side
this
is an
curve, this is the definition. I go up to some point here. That's it.
Well, you have to draw some line somewhere in the space.
No, why?
At some
Why?
physical R.
No, why? Just on Scri plus, I have a time. That's all.
Things don't actually reach Scri plus. You have to draw a line at
No,
some R and say beyond this is
I'm
A,
giving
is
you
A and
I'm giving you a formal definition in the following sense, that assume everything reaches Scri plus eventually. I can then take the state here, which is completely well defined, and break it up into two parts. I can take any state on Scri minus or Scri plus and do this without any reference to the interior. I don't think so. I think in a quantum field theory, okay, we should talk about this more. Maybe I'm wrong. But at least let's take a much simpler situation. I have a quantum field theory in flat space, and I have the vacuum, and I have some excited state. And the excited state locally looks thermal because there's long-range entanglement in it. I think you can make this notion precise that as you include more and more of the state, there is a curve like that which eventually becomes pure again by taking out the infinite contribution by comparing that excited state with the ground state. Now maybe there are additional subtleties in this case. We can come back to that. We can come back. But that's roughly what I have in mind. Okay. Okay, I think I'm down to 15 minutes. I have to do AMPS. And, okay, I'm not going to do Maldacena and Susskind, I think, and I'll do a very perfunctory job of AMPS, but let me try. Right. 4 we can even skip if you like, but 3 we should talk about a little bit, or someone should talk about.
I think we are quite flexible.
Okay, thank you. Okay, so now using these two ideas, let me state in general terms the argument AMPS would like to advance in general terms and then make it more precise, okay? And the general argument they want to make is the following, and this is tied to questions which have already come up. And the general argument is to use a conflict between no drama, okay, the fact that the region around the horizon is a nice place, more or less like the Minkowski vacuum, because after all you're falling in an elevator, there's no gravity, you might as well be in the Minkowski vacuum. So to use a potential conflict between no drama and strong subadditivity. Between no drama and unitarity on the one hand, and try to say that is in conflict with strong subadditivity. Therefore, the postulates of complementarity are contradictory. That is the chain of argument. And what is the argument? Again, somewhat imprecisely, it's this. Suppose we take a black hole which forms from collapse, we wait long enough past the page time so that most of the Hawking evaporation has come out, quanta have come out, okay? Then then it's natural to divide the radiation for an old black hole into the radiation which has come out and the radiation which is which is just barely coming out or will come out, okay? So for an old black hole, divide the radiation roughly into early and late. We are somewhere here. All the radiation which has come out up till here is the early radiation. The radiation which is now coming out, let's say, is late, or which is yet just in virtual quanta near the horizon is the late radiation. So I won't attempt to draw it, but there is early radiation, okay, let's say here, and there's late radiation here, or early here, and late here. And the argument is this, look, if the state is pure, then the late radiation must be entangled with the early radiation, because by itself, Hawking's calculation locally is unlikely to be very wrong. So locally, the radiation probably will look thermal. That is a reasonable thing. So the late radiation, the full state becomes pure because of entanglement. Therefore, the late radiation must be entangled with the early radiation. But now let's come to the region near the horizon. Here is the late radiation, which has not yet made its way out to Scri plus. The early radiation, which came out a little earlier, did make its way to Scri plus. The late radiation hasn't made it. So the late radiation is here. So now we have said, okay, look, the late radiation is going to be entangled with the early radiation. But if, on the other hand, the horizon is a nice, smooth place, then the late radiation must be also entangled with the partners of the Hawking pairs. Let me use the word, and then, so let's say there is a mode here, B, a late radiation mode and its partner, which I call B tilde. Just to state it, B must also be entangled with B tilde because that's what is needed for the region around the horizon to be smooth with no big fluctuations in stress energy. And that can't be because strong subadditivity told us that entanglement is monogamous. If B is entangled with the early radiation, it can't be entangled also with the late radiation. Okay? There are many things I've been imprecise about, I will, but that's the rough structure of the argument they will try to present. Now, just one small thing and then there'll be questions. What do I mean by partner of the Hawking pair? Well, Gautam gave us a derivation of Hawking evaporation, and he constructed the density matrix on the outside, but he has these two sets of modes, right? I forget, what were they called? B and C modes. And the B modes, this is the horizon, the B modes are outside, skirting the horizon, eventually making their way to Scry plus. The C modes are on the other side, close by on the other side, which are also skirting the horizon, but eventually falling into the singularity, okay? And the B and B tilde modes have to be highly correlated with each other if you have something like the Minkowski vacuum. These are the analog of the Rindler modes, the left and right Rindler modes, which have to be highly entangled so that the full state is, in terms of these modes, is a squeeze state, which is the Minkowski vacuum. Okay?
That even when you talk about applying this strong subadditivity involving the B tilde, you don't have to worry about the fact that the horizon entanglement across the horizon decreases when a Hawking pair is emitted, because the horizon radius goes down.
Say that again. I mean,
so you will be using the entanglement between B and B tilde, right?
Yes,
and
yes.
applying it to some strong subadditivity.
Yes,
argument,
yes,
right?
yes.
So in that count, right? I mean, I would think that the entanglement in B and B tilde is naturally thought of as the entanglement in the Hilbert space between the outside, interior, and the exterior of the black hole, right?
Yes.
And that should include the fact that the vacuum entanglement entropy is decreasing because, or changing because the area is changing when the Hawking pair is emitted.
Right. And you're saying if it's formally divergent, is that what you're saying? Yeah, if it's formally divergent, it has to be better defined at least to try and use it. That's true.
And
okay.
if you take the cutoff to be of the order of the Planck scale,
yes,
right, then that change in the entanglement across the horizon is basically the same as log 2. I mean, it's of order 1 for each Hawking pair emission.
Is that right? Because the area changes with the cutoff held fixed.
Yeah, because then it's like that entanglement is like the black hole entropy, right? Delta proportional to m square, and you change the mass by 1 over m, right? That's typical Hawking temperature. So it's of order 1.
I see. Interesting. Okay, that's an interesting point. Let's come to that and other things. But let me state the obvious sort of flaws in the argument, which this is too simplistic a version, but which will lead us to try and refine it. So just to state the argument again, if there is no drama, if the region near the horizon looks like the Minkowski vacuum for an infalling observer, then the outgoing Hawking modes B, okay, for no drama, the modes B, which are outgoing, I just call them outgoing Hawking quanta, and their partners B tilde, which are the partners, are highly correlated or entangled. Sorry, this won't be readable to someone. Are entangled. On the other hand, if the entire state at Scry plus is unitary, then B is entangled with the early radiation.
Sorry, I was saying all the modes inside has a partner outside?
Yes. At least when you do the derivation, that's what you get, right? And if you take Minkowski state and you break it into Rindler modes, that's what happens. So on the other hand, B is entangled with E. the early radiation and this is in conflict with strong subadditivity because entanglement is monogamous. Okay, that's the rough structure, and then we will try to see why it should be made more precise.
I have a question about how you're setting it up. So when you want to apply strong subadditivity, A and B should be maximally entangled. Where is that going in?
Not yet, but that part can be taken into account. For example, actually in the Minkowski vacuum, B tilde and B are maximally entangled. The state together is pure between the left and right Rindler wedges, and yeah, you're right. I'm being imprecise here, but some of those imprecisions can be corrected, and we can try to go. That's exactly what I want to do. Yeah. Okay. Now there's an obvious. I've been too quick in an obvious fact that we can do quantum mechanics in the usual way to describe the experiments the freely falling observer is doing. Okay. If you try to believe in quantum mechanics and you want to use equivalence, etc., this much seems reasonable. There should be some quantum mechanical description, not globally, just for some freely falling observer. If you do that, then we are going to show that you reach a contradiction. Okay, and so that's a slightly more precise version. So they say, take the early, and I think some people will find fault that you can make the argument more precise, which we'll try to do, but let me state it. Take the early radiation. Okay, assume that, of course, you have to wait till the black hole completely evaporates for the state to be pure. But if the black hole is mostly evaporated and it's pretty old, then then the full state between the late and early radiation is almost completely pure. Okay, if it were completely pure take a bit. So let's say take a bit, just to make it a qubit, let's say, in the late radiation, which I'm calling this mode B. Now, if the full radiation had come out, the full state would be pure. Then it is entangled with the rest of the radiation, and you can always and let's say Hawking is correct as far as local bits, etc., are concerned. Then it will be close to maximally entangled, with the rest of the system. Or maybe with some thermal factor, is it? Okay, maybe with some thermal factor. Okay, but a local bit will be close to maximally, I think, entangled. Then you can, if you have a pure system where a single bit is maximally entangled, you can always do an operation wherein you extract one bit, okay, from the rest of the radiation, which carries the entanglement with B. Okay, so take a bit of the late radiation, extract from early radiation a bit, let's call it E, which is maximally entangled with B. Okay. Now take a freely falling observer. He's gathered the E, all the early radiation. He does this measurement and extracts a bit E. Sorry. He extracts E. He falls in his elevator. Along the way, he picks up B. I should draw a picture. Let me get rid of all this now. Here is the early. Here is the late. There is an observer. He gathers some of the early radiation, falls in, picks up B, falls in, and now when he falls in, he has access to the interior, and he picks up B tilde, okay, the partner. Okay, so extracts from early radiation E, and now take a infalling observer. Who takes E and B and falls in, and also gathers B tilde. He manages to fall in through the horizon because we are assuming, as per the postulates of complementarity, that there's no drama, so you should be able to fall in. So he falls in, he gathers B tilde. Now we have a contradiction. E and B are maximally entangled. Locally, B in the radiation outside has nearly maximal entropy, so it would be maximally entangled with E. So E and B are maximally entangled, but if the horizon is a smooth place, B and B tilde would also have to be entangled, okay? And that is in conflict. Very, very rough usage of the word, but roughly the idea is can do a measurement which detects B tilde and the correlation of, I suppose, B tilde with B. Or, you don't have to do that. Just constructs a description of the region around the horizon.
Infalling observer, you see vacuum, right? The infalling observer is supposed to see vacuum.
It sees vacuum, so that's right. So this is harder to do. But let's say he's trying to do quantum field theory.
Yes.
He knows that that B is entangled with E, and he would therefore not be able to come up with a description for the region around the horizon where the B tilde modes would be entangled
but
with E. Even
the
though
B
I
tilde
agree
and B doesn't exist as actually particle-like states for the infalling observer, right?
If you allow me to be Baroque, he falls in and switches off and turns on a huge rocket. And now he's hovering at the horizon, the B tilde quanta are real for him. Okay. Yeah, okay. This is not something he will see easily. Gathering this quanta is not easy. But it's true, at least if he's trying to set up a quantum field theory description, having made this measurement, he would have a hard time doing it consistent with the usual, with strong subadditivity, etc.
Having done what measurement?
Having measured, having extracted from the early radiation the bit E.
Yes.
And having, now you may say he even has trouble extracting B, actually.
Yeah, where is the infalling observer, right?
So what he would do, is, okay, let's say the bit, we'll have to work out time scales, but let's say the bit has made its way far, B also, is late but not that late, and has come out some distance. So then it looks more or less
So
like
the infalling observer is not freely falling, but somehow in a rocket.
Yeah, he starts at rest. Let's say he starts at rest. He starts at rest very far away. We won't object to that. There he gathers E and B. Then he falls in. Now he's falling in, so your objection for B tilde applies. But I think he turns on a rocket at that stage. Or he tries to, no, but I mean, it's a serious point. It is a serious point.
He can have somebody who's sitting and gathering B tilde and somebody gathering
And yeah, good. And you can sharpen many of these things by saying there's a partner, the partner does part of the experiment, and they have enough time to exchange their information. Or I think it's a serious point.
But you are really saying that even after falling in, you have to slow down and detect something. Meaning you basically see the Unruh effect, right? That's what you are saying.
I think for actually seeing B tilde, you would have to do that.
So it's like Unruh effect is in contradiction with this whole thing, because if you just freely fall in, you don't see anything.
Yeah, that is true, but you have seen, let's say, the B quanta. So you want to construct a description of Hawking evaporation.
You have seen the B quanta by,
when you were outside and, let's say, not falling in.
falling in.
You want to construct a description for the Hawking evaporation. And, you will have to assume that you can break the region around the Minkowski vacuum into Rindler-like modes, even though it might be hard to do that.
Here is how someone could do this, although I think the central objection is in extracting.
Yeah.
Let's say there's somebody who's hopping at the horizon. So there are three people. There's somebody who sits at the horizon who connects the bit B and determines its spin. Let's say they only want to determine the spin. There's a partner behind the horizon who determines also the spin. And these two are completely correlated because the person in front has determined the spin.
So the partner behind also is
hopping at the horizon. So they're two hopping at the horizon. Now there's somebody else who collects all the late radiation who falls in. As he falls in, this guy hands him this first spin. When he goes behind the horizon, he hands him the second spin. Now it looks like he has three spins. He has three ways of determining the spin. You can determine the spin of B using E or using the thing tangent behind the horizon. So you can have two partners, one hovering just outside, one hovering just inside, and then he can collect it. But I think the central problem is that extracting E is an impossible.
So let me come to that. Let me come to that. And I don't know, maybe I just, let me come to that, at least complete my amps, this part, and then we'll see. Now, you know, one objection to this might be, look, you had to do an experiment here, which is extract from the early radiation this bit E, okay? Maybe that is what is leading to this problem and the conclusion that you have a firewall. Suppose you didn't do that measurement, okay? Then where's the contradiction, all right? So that could be what is really going on. But to that, AMPS argue that you can do the experiment late enough so that its consequences don't apply to someone who falls in first, but is then communicated the answer to this experiment. Okay?
What is the argument? So this is this hard-headed argument, right?
No, that's a little different. So the idea is you have Alice who falls in. We'll have to work out time scales, which I actually haven't done for this particular one. I won't attempt it here. The idea is Alice falls in. Then Bob does this measurement of extraction and sends the signal into Alice. Then Alice has seen a nice smooth horizon, but learns that, oh, B was entangled with E, and finds she can't construct a consistent description. And so what they tried to say was that you can do this measurement so far away, roughly, that the result of this measurement can't be communicated to near horizon region fast enough. And therefore, whether you're doing the measurement or not can't affect the outcome or what you see when you fall through a horizon. But on the other hand, if you do the measurement and you could have communicated it, you would be led to a contradiction. Therefore, there must always be a contradiction with complementarity, and there should be a firewall as the way out. Okay, so there is this this part of it, that maybe the extraction could be affecting the result, but they try to argue that causality on the outside, the fact that you can do it far away, it does not affect it. Now, various people have tried to, come up with other versions of this argument, one of which Ashok mentioned, which is maybe extracting the bit takes, or whatever, some analog of this measurement, which is complicated, takes a long time. And it takes such a long time that by the time you extract the bit, the black hole has completely evaporated anyway, so there's not a contradiction. I don't think that argument per se is very strong. For various reasons, you can embed things in ADS, you can slow down clocks and speed up clocks, but still it's worth taking into account. Another version of this is that extracting in ADS, talking with Suvrat about, is that extracting this bit really involves computing a very complicated correlator, and maybe semi-classical physics can break down. Maybe that's why these departures allow you to communicate between the inside and outside. I think that's very interesting. I think it would be nice to sharpen that. So there are some ways possibly out. I'm not saying the AMPS argument is airtight, but this is the argument, and I think it's worth taking it seriously because it really tries to poke sort of very deeply into this idea of complementarity. Okay, now what I wanted to do was to review Maldacena and Susskind, but I think it depends on what you like. If you like 10 minutes, I can do that. If you don't, I can stop. And we know we have lunch, so.
I think we have approximately 10 minutes till 1 o'clock.
Okay. Is that okay? So let me say this. I'm sure Suvrat will cover some of this. What I have given is perhaps not the strongest of AMPS arguments to many practitioners in the subject. There are a whole set of other arguments, but I think I'll leave that to Suvrat to cover. And let me try to give you a flavor for what Maldacena and Susskind did and how they try to shed light on this problem.
There is a more outrageous statement due to Polchinski that there is no inside space-time black hole.
Yes, okay. So that's right. So there are other versions of the argument, and the other versions of the argument are roughly as follows. The other versions of the argument are roughly as follows. Let's say information comes out, and that means whether you threw in the Britannica or the Shabdakosh is actually encoded in the outside. That means the interior, B, let's say, is actually encoded in the outside region, radiation in particular. So B is encoded in outside radiation. And many of the other arguments of AMPS try to say, look, we just can't come up with a sensible way of doing this coding. If you have operators on the inside, you try to map them to the outside so that the algebra is preserved. That doesn't seem possible. If you try to do this in the context of ADS CFT, that doesn't seem possible, and so on and so forth. And that's the spirit of some of their other arguments. Some would say stronger arguments. I think Surat will probably cover these. And so I don't do that here. But part of Polchinski's statement that you just can't encode the interior in a sensible way is coming from that. They're trying to critique the fact that there's an interior by saying there's no way to encode the information about the interior in the outside, therefore there can't be an interior. So that's the spirit of it. But only it was very brief because I have 10 minutes.
I think it's completely relevant to the premise of this thing. Since the crucial bit seems to be the monogamy of entanglement, and since we know that we have to describe it in terms of quantum field theory, to the best of my knowledge, there is no proof of monogamy of entanglement within quantum field theory. So I was just wondering, what is, is that an assumption?
You
or is
mean
that
strong subadditivity doesn't hold?
yeah, computationally, it's, I don't think there is a proof.
Finite dimensional Hilbert spaces, you could prove it. So there's some
within
complication
the
about a
premise of
cutoff.
quantum mechanics, I think there is a proof of strong subadditivity. But
yeah, yeah,
for a finite dimensional.
yeah. So yeah. So maybe there are some subtleties associated with the UV cutoff. I agree. That's that's an issue. Some of them we might be able to take care of. But okay, it's worth talking about. Okay, so Maldacena and Polchinski introduce a new element into the discussion. Oh, I get them all mixed up, sorry. So M and S, and they introduce a new element in the discussion, new compared to what we have talked so far, and that is the very interesting set of developments that entanglement and space-time geometry are deeply related. Are deeply connected, these ideas. In fact, a slogan one could coin is that space-time geometrizes entanglement, okay? In a sense, space-time arises because of entanglement. This is just a slogan, but it's a kind of interesting idea. And they try to bring to bear this kind of an idea to the information question that we are studying. So let me very quickly tell you how that happens. But what is their bottom line at the end? Their bottom line is the following. They would like to claim, and I think they have good arguments, that when they look at various situations, a firewall does not have to form, okay? But on the other hand, the arguments of AMPS, etc., do carry weight because a firewall can sometimes form. Depending on what you do to the early radiation, depending on what kind of experiment you do on it, you can sometimes get a firewall. And how can you get a firewall if AMPS, etc., argued that you're not allowed to do that because of locality, because you can do the experiment very far away, and so on. They show how you can do that and what are the violations of locality responsible for that. So that's very interesting. So the bottom line is firewalls don't have to form. The horizon can be a smooth place. But the arguments of AMPS, etc., should be taken seriously. There's not some sort of obvious kind of drawback in them taken seriously, because firewalls, they can sometimes form. Okay, so that's their bottom line. What do they actually do? Their analysis begins by studying actually an eternal black hole, which Gautam ran out of time and couldn't cover. And actually, they study the eternal. Their arguments, I think, in my mind, are most precise in the context of ADS space, although they try to extrapolate from that to flat space, and it's a plausible extrapolation. But most, I think, firm in ADS space. And they start by considering the eternal black hole in ADS space, which was looked at earlier in Maldasena's beautiful paper on the subject. And here is the space-time, sorry, very bad diagram, I apologize. These upper lines are actually singularities. So this is in ADS space, the eternal black hole. You have two boundaries now, not just one boundary. And you have a CFT1 on one boundary and a CFT2 as per the ADS CFT correspondence on the other boundary of this two-sided system. And Maldacena argued, based on work of Israel and so on, although Israel's paper itself I didn't find very illuminating in this, anyway, argued that in fact the dual to this space-time geometry is a pure state. You know, the geometry has black holes in it. Each side sees a black hole at some temperature, but in fact the full state describing this system in the tensor product Hilbert space of the two conformal field theories is a pure state. Okay, so this eternal black hole geometry is dual to a pure state in the full Hilbert space, which is the tensor product of Hilbert space of CFT1 times 2. And what is the pure state? It's called this famous thermofield double. Let n denote eigenstates of energy in the first Hilbert space, and I use the same label in the second Hilbert space. Sum over all such tensor product energy eigenstates with a weight e to the minus beta times their energy over 2, where beta is the temperature of the black hole. And this pure state, it is a pure state, you see, is actually dual to this geometry. Okay? Several obvious checks. If you trace over one of them, you get the thermal density matrix for the remaining CFT. That is in accord with the fact that this CFT really, in any reasonable experiment, only sees this region of the space-time where you have just a single black hole, etc. And but here in this state, it's pure, but there's entanglement between the two CFTs. Okay, this is the crucial point. The two CFTs are entangled, which is why each CFT sees a thermal density matrix. And this entanglement gets geometrized very beautifully in the gravity dual in the form of the Einstein-Rosen bridge. Okay, as we all know in the eternal geometry, it's true in the Kruskal extension in flat space. For the Schwarzschild geometry, it's true here in ADS space. If you look at, for example, the geometry, the spatial slice which cuts across at the moment of time symmetry, and reaches here at the bifurcating two spheres, it's called, then this looks like a Einstein-Rosen bridge. It narrows to this point, P. This is the asymptotic 1 region, and then opens out again into the other asymptotic region. Okay, and it's this fact that the two black hole horizons meet up. Okay, this fact that they meet up and they become one black hole horizon in a sense is what is dual to the fact that in the field theory you have entanglement. The bridge geometrizes it. We know you can't use the bridge to go from one CFT to the other. These are space-like separated. That corresponds to the fact that if you have EPR-like correlations, you can't use them to actually send signals. Okay, and so beautifully again, the space-like separation is tied to this feature. But there's a very interesting fact, which is while you can't go from this region to this region, you can have an observer here who falls in, and you can have an observer, let's call it Alice, you have Bob, and you fall in, and they can meet in the upper plane, in this upper region, in the upper wedge. Okay? And so the ER bridge leads to an interesting possibility that you can go fall in and then meet up with somebody from the other side. Okay? So this is a very interesting fact and a very interesting connection. What does it, in the remaining 5 minutes, what does it have to do with the information puzzle that we've been talking about? Okay, roughly the idea these people had was the following. Let's take a single-sided to begin with situation and somehow have a black hole in ADS space which evaporates. Let's wait till it gets old enough. Okay, say it gets to be of the page gets to be at the page time. Now take all the early radiation and transfer it somehow to a second CFT. Okay, so now you have two entangled CFTs, and you have a situation which, let's say, can be made into this. Having come to such a two entangled CFT situation, we know what the field, what the gravity dual is, and let's use that gravity dual to ask, do we have firewalls or not? Okay, so they do, one sec, like AMPS, they also want to do an experiment. They also do actually a rather complicated experiment, but one where they're going to transfer, and I'll tell you how you do that, the entanglement to a second CFT, and from there then end up trying to construct a situation like this and ask whether you have a firewall. Yeah, go ahead.
This construction, which one in each two had to have equal dimension?
Had to have equal, yes.
So where is the other? Sorry. In the other situation, you could choose the bifurcation point wherever you like along scribe class. So it's hard to arrange that the dimensions are always equal.
Yeah, that's true. That's true. And to translate the collapsing situation to literally this one, what you'll have to, let me just talk about it, but what you'll have to do is stop the, roughly speaking, you could try to do it various ways, but the simplest would be to stop it at the page time and then transfer that entanglement to the second CFT. And then you would have a situation like this. Otherwise, you might have, even if the two CFTs are identical and they have the same Hilbert space, you might not come to a state which is the thermofield double state in general. So, okay, so the basic idea was something like this. As you know, black holes don't actually evaporate in ADS space if you just had the standard situation, which now let me not try to drive. If you have a black hole in just ADS space, not this double-sided situation, just one boundary, black holes don't really evaporate. But what really happens is, let's say something collapses to form a black hole. The black hole does start giving out Hawking quanta. Hawking's calculation is not wrong. But eventually those quanta get to the boundary. And at the boundary, we don't want to lose energy. We always put reflecting boundary conditions, so the quanta fall back in, get evaporated, and pretty soon what you have is a stable black hole in equilibrium with the radiation outside, okay? And so the idea was, let's take a, oh, well, let me draw it. Here is actually R equal to 0, not the other side. This is the boundary of ADS space. Here is some collapse situation in ADS space. Form a horizon. So this is R equals 0 as it was in that diagram I drew there in flat space. It's not the other boundary of ADS space. Now this black hole starts evaporating. You gather the quanta in the CFT. Here sits a CFT. And then literally, I mean not literally but figuratively, connect this CFT with some wire to a second CFT. Okay? And wait till enough energy, so the energy which hits this conformal field theory is sent to the other one. You wait long enough, there's equipartition of energy, but the state is pure. You started with the pure state, the full state of the system. How do you connect them? If you want, you have some interaction Hamiltonian, some coupling which you can make time dependent, time some operator in the first theory, some operator in the second theory, okay, some interaction like that, which is a unitary, it's a Hermitian operator. So the evolution of the system is unitary in the full Hilbert space, and you start with a pure state, which is some excited state in CFT1 and the vacuum in CFT2. In the end, you'll have a pure state. And you can arrange it, it might take some doing, but you can arrange it so that that tensor product state in the two CFTs is this thermofield double. Okay, that was their point. That look, you can conceive of an experiment, all right, might not be very easy to do, because even if the entropy has been equally partitioned, etc., it may not quite be the thermofield double state, but you can conceive of a situation where it is the thermofield double state. And if it is the thermofield double state, then given the fact that the thermofield double state is the eternal black hole geometry for which there's good evidence, although I don't know if it's IMCAS, but I think it's good evidence, we can now say, is there a firewall or not? And the point is that here in this situation, you have nice smooth horizons with no firewall. So therefore, at the end of this experiment, admittedly complicated one, where you took the early radiation and moved that in effect into the other CFT, the conclusion is if the state in H1 cross H2 is the thermofield double. Then a smooth horizon. For example, this horizon for the first CFT would be smooth and no firewall. But on the other hand, you could do other things. You could manipulate the early radiation that goes into the second CFT by doing further operations on it. If you did suitable operations that in this picture, even though you're really constructing the state in a sense here, you could construct a state here which is the analog of having turned on a pulse of light, high energy light at an early time. So you do construct the state here which corresponds to that gravity dual. And if you did those manipulations on the early radiation, then look what happens as far as the wedge, right wedge is concerned. Of course, nothing changes. But now when somebody falls in, he sees that huge intensity pulse beam and he gets fried. And so you don't have to have a firewall. But depending on what you do to the early radiation, you can get a firewall. Okay? How was it that they managed to avoid the arguments of AMPS? They have managed to avoid them. AMPS said, look, you're doing the experiment so far away, its outcome can't decide whether you have a firewall or not. If you grant us that sometimes you have a firewall, that's enough to say you must always have a firewall because you don't have time to communicate that information of the measurement. It avoids it because you get a shortcut, in a sense, through space-time provided by the Einstein-Rosen bridge. Okay? If you didn't have the bridge, these two CFTs could be very far apart from each other. One could be here, the other could be in Andromeda. They would have no way to communicate. But a bridge opens up. The moment you entangle them, you open up an Einstein bridge. That bridge can change the results of measurements after you fall in through the horizon. It can't change the measurements outside, but it can change them inside. And so it's this fact that you have a radical departure from the background geometry because of the bridge opening up that is really responsible for evading the AMPS argument. Okay? So they do other things, but what they do in that paper. Let me end with a summary. I'm really sorry, which will take exactly a minute. My summary of all this, which could be wrong, and some of you know much more about it, but let me just say in one word that my summary is, I think what makes the information puzzle so deep and profound is that there is a real tension between unitarity and the principle of equivalence. There's a real, you see this all through, there's a real tension, and I don't think the AMPS and related developments have led to a result of a firewall which is true necessarily. I don't believe it myself, but it at least heightens the awareness of this tension, and I think it brings to fore the point that one should really think about it much more seriously. So let me just stop there.